This lesson is on forms of quadratic equations. Quadratic equations come in three different forms. There's standard form, there is vertex form, and then there's factored form, which is also known as zeros form and is also known as x-intercept form. So these three here are interchangeable in terms of the name. Standard form is y equals ax squared plus bx plus c. Vertex form is a x minus h all squared plus k. And factored zeros, x-intercept form, they look like this. So y equals a x minus x s, times x minus t. So what we're going to look at is that these three forms, although they look very different, when you put the respective coefficients or constant in, so when you have an a, b, or a c, or the a, h, and k, or a, s, and t, although they look very different, they actually represent the same quadratic relation. So now what we'll do is go through an example. Here we have the three different algebraic representations of the same quadratic relation. Here we have standard form, which is y equals x squared minus 2x minus 8. Vertex form, which is y equals x minus 1 all squared minus 9. And factored form, which is y equals x minus 4 times x plus 2. Now, if these three represent the same quadratic relation, they should have the same table of values. So we'll start with standard form, filling in when x is negative 3, 9 plus 6 is 15, 15 minus 8 is 7. 4 plus 4 is 8, 8 minus 8 is 0. Then we have 1 plus 2 is 3, 3 minus 8 is minus 5. 0 minus 0 is 0, minus 8 is minus 8. Then 1 minus 2 is minus 1, minus 8 is minus 9. Then we'll have 4. 4 minus 4 is 0, 0 minus 8 is minus 8. And then finally, when x is 3, we have 9. 9 minus 6 is 3. 3 minus 8 is minus 5. Then for vertex form, I have minus 3 minus 1, which is minus 4 all squared is 16 minus 9, which again is 7. Look at that, as expected. Minus 2 minus 1 is minus 3. Minus 3 all squared is 9. 9 minus 9 is 0. Then minus 1 is minus 2, which all squared is 4. 4 minus 9 is minus 5. Then 0 minus 1 is negative 1. Negative 1 all squared is 1. Minus 9 is minus 8. Then 1 minus 1 is 0. 0 squared is still 0. Minus 9 is minus 9. Then for 2, 2 minus 1 is 1. 1 squared is 1. 1 minus 9 is minus 8. And then 3 minus 1 is 2. 2 squared is 4. 4 minus 9 is minus 5. So if we look at that, as expected, if they are representing the same relation, the standard form, so this form here and this form here, they have identical tables of values. And if this version, this factored form, or this equation here represents the same quadratic relation, then its table of values should be the same as the other two. So we will fill in that table of values right now. So minus 3 minus 4 is minus 7. Minus 3 plus 2 is minus 1. So minus 7 times minus 1 is 7. All right, so now when x is negative 2. Negative 2, so minus 2 minus 4 is minus 6. Minus 2 plus 2 is 0. Minus 6 times 0 is 0. Minus 1 minus 4 is minus 5. Times minus 1 plus 2, which is 1, which is minus 5. 0 minus 4 is negative 4. Times 2 is negative 8. 1 minus 4 is negative 3. 1 plus 2 is 3, so we have negative 9. Then minus 2 times 4 is minus 8. That doesn't look like a very good 8. There we go. And then we have 3 minus 4, which is negative 1. And 3 plus 2 is 5. So minus 1 times minus 5. Sorry, minus 1 times 5 is minus 5. So there we have it. We have the 3 different forms of a quadratic equation that are representing the same quadratic relation. The table of values are identical. And if we looked at the graph would also, of these 3 different equations, would be the same. So here we have the graph of the quadratic relation. We also have our 3 different forms. And we have the table of values that represents the quadratic relation. And this table of values, it's the same one from that we calculated, but I've just added on 2 extra points here, so 4, 0 and 5, 7. And what I'd like to do now is show how the key features or the properties of our quadratic relation, so we can pick those out not only from the graph, also see where they connect to the table of values and connect to our algebraic representations. So one of the features of a quadratic relation in terms of its graph is that its graph is symmetrical. So if we look here, if I drew a line down the center of this graph, which I will do, it cuts this graph in half. And so if I took this side here and I folded it along this line, it would lay right on top of this side here. And so this graph is considered symmetrical. And this line here that goes down the center of it is the axis of symmetry. That is not very nicely written. So I will write it again. Alrighty. Axis of symmetry. Now, the axis of symmetry has an equation, and since this is a vertical line, and it goes through where x is equal to 1, then the equation is x equals 1. And that's because no matter what the value of y is along this line, x will always be equal to 1. So the axis of symmetry, one other identifying feature is that we have what we call symmetric points on either side. So I know that this point here and this point here are equal distance from the axis of symmetry. because it's symmetrical. So these are symmetric points. Same with this point here and this point here. They're the same distance from the axis of symmetry, so they're symmetric points. All right, so let's identify some of the other properties. We have the vertex. The vertex is either the lowest point or the highest point on the graph, depending on the direction of opening. This particular graph opens up, and so here we have the vertex down here. This is the vertex. And how we can identify the vertex from the table of values is that if we know we have symmetric points on a graph, and how we can tell if we do have symmetric points or their y values are the same. So here 5 and -3, they're symmetric points because 7 is the same y value. -2 and 4, -1 and 3, 0 and 2, and here this is halfway in between these symmetric points. So this is where our vertex is. Now what you should also notice is that the x-coordinate of the vertex is the same as the axis of symmetry. And so we can always pick out the axis of symmetry from the table of values, because this will be, I'm going to label it AOS, the x-coordinate of the vertex. Okay, now other properties of this quadratic relation are the x-intercepts. The x-intercepts are where it crosses the x-axis, so that's when y is equal to 0. So we can pick those out here and here. So those are the x-intercepts. The y-intercept is where it crosses the y-axis. So that is here. And that is when x is equal to 0. So if I go to the table of values and find where x is equal to 0, which is right here, then I know that this is where my y-intercept is. So I have the x-intercepts, the y-intercept, the vertex, the axis of symmetry and its equation. And if we look here, when we talk about direction of opening, it opens up. All right, so it's a happy face. It opens up. And one other thing we should be picking out is, because this opens up, it has, its vertex has a minimum value. And the minimum value will be its lowest y value. The lowest y value here would be the y-coordinate of the vertex, which is here. So this is the minimum, which is the lowest y value, in this case because the graph opens up. All right. So what we'll do next is we'll look at, okay, well, I can pick out properties from this graph. I can pick out properties from the table of values as long as it contains that information. But then how do we pick out that information from these three forms of equations? And that's really important, is trying to pick out, you know, the vertex, the x-intercepts, the y-intercept, the axis of symmetry, the direction of opening, and all those properties. And some of these forms are more useful than others, and that's what we'll look at next. One thing that you should be noticing is that there are some patterns with what we see here and those properties, what we see here and those properties, and what we see here. There are some things that are more easily identified depending on the form, and that's where knowing which form to use can help you determine those properties more easily. So if we look at standard form, if you'll notice, we can easily identify what the y-intercept is, because that's when x is 0. So this would be 0 minus 0 minus 8 is minus 8. If we look at this form, which is vertex form, and we consider the name of this form, we should be able to pick out the vertex fairly easily. And if you look at this, you'll notice that this minus 9 corresponds to the y-coordinate of the vertex. This here, although it's a 1, the vertex has an x-coordinate that's a positive 1. So there's something slightly different here, but it still relates to the vertex. And then if we look at the x-intercepts, our x-intercepts are at -2 and 4. Those numbers are here also, but they're the opposite sign. And so what we again will do next is look at, well, how do I pick these numbers out and relate it to the different properties, and then what other information can I get? So now looking at standard form. So in terms of properties, we have the y-intercept, and that is when x is equal to 0. So what I can do is substitute in 0 for x and solve for y. So I have y equals 0 squared minus 2 times 0 minus 8, which is 0 minus 0 minus 8, which is minus 8. Okay, great. I got the the y-intercept. Now, let's see if we can figure out what the x-intercepts are. And the x-intercepts are when y is 0. So let's substitute in. So x-intercepts, and that's when y is equal to 0. So as we know how to substitute, I'll have 0 equals x squared minus 2x minus 8. And most of us think, okay, well, I'm just going to solve for x. So if we go through that process, that means that I'm going to add 8 to both sides because I want to isolate x. So to get rid of this term here, I have to add 8 to both sides. So I have 8 equals x squared minus 2x. Well, now what do I do? Well, I've got an x squared and a 2x term, and I can't really combine these two because they aren't like terms. And so this is where I get kind of stuck, and it's not really, we're not really able to find the x-intercepts in this form. We're kind of stuck. So then you have to think, well, now what do I do? Can I find out any other properties from this form? And when it comes down to it, there's only one other property you can determine from this form, and that is what direction it opens. And that comes from whether this term here is positive or negative. So if this term's positive, it's going to open up. And if this term's negative, it's going to open down. So since this is positive, our direction of opening and that's up. Okay, now we'll look at vertex form. So going through the same process, so to find the y-intercept, so this is when x equals 0. So I have y equals 0 minus 1 all squared minus 9, which is minus 1 all squared minus 9, which is minus 8. So our y-intercept is at 0 minus 8. Okay, how about the x-intercepts? So the x-intercepts, this is when y equals 0. So I have 0 equals x minus 1 all squared minus 9. And all I'm going to do is rearrange this. So I have to add 9 to both sides. So I have 9 equals x minus 1 all squared. And here, my next step is to get rid of the square root. And what we actually have here is we have two possible square roots, because not only is the square root of 9 3, but it is also minus 3, because minus 3 times minus 3 is 9. So how we write this is we have plus or minus the square root of 9 equals x minus 1. So I'm going to bring this all the way up here. So to continue solving this, I have two possibilities. I have the positive square root of 9 equals x minus 1. And I also have the negative root of 9. It's not a very good 9. There's a 9. Is x minus 1. So to solve this, I have 3 x minus 1. I'm going to add 1 to both sides, and I have x equals 4. And then on this side, I have minus 3 is x minus 1. I'm going to add 1 to both sides, and I have minus 2 equals x. And if you remember from our graph and from our table of values, these are, in fact, our x-intercepts. Our x-intercepts we saw were at 4 and negative 2. So those are our two x-intercepts. So we have 4, 0 and minus 2, 0. So we have the y-intercept, we have the x-intercepts. Now we need to pick out the vertex. And since this is vertex form, the vertex is fairly easy to pick out. So how it works is this here will be the y-coordinate of the vertex, and this here is the x-coordinate of the vertex, but the sign changes. And the reason for that you will find out more clearly when we look at transformations of quadratic relations. But at this point in time, I'm just going to ask you to trust me on this, is that my vertex, so this is the x-coordinate, and this is the y-coordinate of the vertex. So I'm actually going to do negative x-coordinate because you're going to end up changing the sign. So the vertex is 1, negative 9. And so what I've done is I've changed the sign on this and then kept the sign on this. So we have our x-intercept, which is at 0, negative 8, our y-intercept, our two x-intercepts, which are at 4, 0, negative 2, 0. We have our vertex, which is at 1, negative 9. And so now from our vertex, we can actually pick out our axis of symmetry, as well as our maximum or minimum value. So this is the axis of symmetry. Or affectionately known as the AOS, which is x equals 1. Now this particular quadratic relation, it does open up. And how we tell is again at the very front of this. So here, this is positive. And if there was a negative out here, the direction would open down. So the direction of opening is up. So that means that we have a minimum value. And that is here. So this is our minimum value. Which is y equals minus 9. All right, so recap again. We have our y-intercept at 0, -8. We have two x-intercepts at 4, 0, -2, 0. Our vertex is 1, minus 9. Our axis of symmetry is where x is equal to 1. We have our minimum value, which is y is equal to -9, and we know the direction of opening is up, and that's because this here is positive. So what's interesting is that in vertex form, we can actually get all of the properties of our quadratic relation, where from standard form, the only two that we could get was the direction of opening and the y-intercept. So now we're going to move on to factored form, or zeros form, or x-intercept form, and see what properties we can get from that form of equation. Okay, so now we'll look at factored, or x-intercept, or zeros form, and see what properties we can get from that. So starting again with the y-intercept, so this is when x equals 0. So I substitute in 0 for x. So we have minus 4 times 2, which is minus 8, as expected. So that is 0 minus 8. Now, x-intercepts. Now this is when y equals 0. So when I set y to 0, I have to solve this. It's not as easily solved or directly solved like we found with vertex form, but if we think here, well, because this is being multiplied to this, if one of these two are 0, then that would make the whole thing 0. So if this all added up to 0, then 0 times all of this, no matter what this is 0. And same with this. If this was all 0 and I multiplied it to whatever this ended up being, then we'd have 0 times whatever, and we would end up with 0. So we could find out the value of x. So what I want to do is find a value for x that will make either this 0 or this 0. And how I do that is I set this to 0 and I solve for x. So x equals 4. And I set this to 0 and I solve x is minus 2. So what that means is that if x is 4, because 4 minus 4 is 0, and then 4 plus 2 is 6, so 0 times 6 is 0. So that is true. My left-hand side is equal to what my right-hand side would be. If I set x to minus 2, so I'd have minus 2 minus 4 is minus 6. Minus 2 plus 2 is 0, so I'd have minus 6 times 0 will give me 0. So again, left-hand side equals right-hand side, and we know that that is true. So that's how we can find out the zeros. Now, a common mistake is that students just think, okay, well, I'm just going to change the sign of this. Well, that doesn't always work. It only works if the coefficient in front of my x is a 1. But if it's something other than a 1, it doesn't work. So you have to be very, very cautious with that. So next what we're going to do is we have to find the other properties of the vertex as well as the axis of symmetry. One thing we know about the x-intercepts is that these two are symmetric points. So symmetric points, as we've talked about, they are equal distance from the axis of symmetry. So if I can find the halfway point between here and here, I can find the equation for the axis of symmetry. All right, so the axis of symmetry. So it's the halfway point between 4 and -2. So we know that we go 4 plus -2, all divided by 2, which is 2 over 2, which is 1. So that means my equation for my axis of symmetry is x equals 1. We also know that the equation for the axis of symmetry is the x-coordinate of the vertex, or the vertex goes through there. X equals 1 is the x-coordinate of the vertex, so if I know what the x-coordinate of the vertex is, I can easily find the y-coordinate of the vertex by substituting that in for the two x's and solving for y. So I'm going to do that now. So vertex, that will be when x equals 1 in this case. That's not always the case. You have to find the axis of symmetry first. So that is y equals 1 minus 4 times 1 plus 2. So 1 minus 4 is -3. 1 plus 2 is 3. And look at that. Y equals -9. So the vertex is at 1, -9, as expected, as we saw with the graph and the table of values. And when we were looking at vertex form, it's the same. So again, if these three forms represent the same quadratic relation, we should have the same properties. The direction of opening, again, as with the other ones, if the number in front of here, or if this is positive, then it opens up. If it's negative, it opens down. Since this is positive, it opens up. And last but not least, to get the maximum or minimum, in this case, again, we have a minimum because it opens up. Minimum will be the y-coordinate of the vertex, so the minimum is y equals -9. So this is how we get the various properties from the different forms of equations. And what we've seen is that some forms are more useful than another form. All right, so when we have standard form, which is y equals a, x squared plus bx plus c, in our case, what that looks like, whoops, is y equals x squared minus 2x minus 8. The only real information out of all the properties that we could find was the direction of opening as well as the y-intercept. So we know that this here, the -8, this is our y-intercept. And that's when x equals 0, because essentially we have 0 minus 0 minus 8, which is -8. Here we have our a value. Our a value is 1. It's positive, so our direction of opening is up. And that's because a is positive. When we look at vertex form, we actually found we could find all of the properties. So that was y equals a, x minus h all squared plus k, and h and k is the vertex. So in our case, we have x minus 1 all squared minus 9. So my vertex is 1, -9. Now we can find all of the other properties Again, to find the y-intercept, you set x to 0 and solve. To find the x-intercept, you set y to 0 and solve. So you would set y to 0 and solve. Vertex, here it is. Axis of symmetry, x-coordinate of the vertex. Minimum value, -9. And the reason that we know that it opens up, again, this a value is 1 here, and it's positive, so it opens up. Now, factored form or zeros form. X-intercept form. So that is y equals a, x minus s, x minus t. In our case, we had x minus 4, x plus 2. So when we had factored form, this form we could also find all of the properties. The y-intercept when x is 0. The x-intercepts, which is when y is 0, and that's where we set each factor to 0 and solved. Axis of symmetry is halfway between the two zeros. And then the vertex, we just sub in the x-coordinate of the vertex, or the axis of symmetry, and to solve for the y-coordinate of the vertex. And again here, our a value is 1, and it's positive, so it opens up. So, as a recap one more time, all we can find out from standard form is the direction of opening and the y-intercept. For vertex form, we can find everything. And factored form, everything. So our two most useful forms are vertex form and factored form. Standard, not so much. And what we'll see in another lesson is that sometimes you're only given standard form, so how do I switch from this form to either this form or this form to help me find all the properties or answer problems associated with quadratic relations?